Hello, so today we will learn more about theorems that relates homomorphisms with subgroups, and these are the theorems. Number one, you see here you have 6 theorems, 5 and 6. So what I will be teaching you today is theorem number 6. Theorem number 6 is very important, and also theorem number 4. Theorem 1, 2 and 3, you can try them as your own as exercises, and also number 5, you can try it as an exercise. So let's see what does the theorem say, what all of these theorems say. So you have a homomorphism f from G to G dash, and it is on 2, and we are given that H is a subgroup of G. We are given that H dash is a subgroup of G dash. So you see here theorem 1 is concerned about the pre-image, and theorem 5 is concerned about the image. So before going into the theorem number 4 and number 6, which I will do, first of all you need to have an idea of what an image and pre-image of a set is. So what are we given? We are given that We are given that H is a subgroup of G. So this H, it is a subgroup of G. And because any subgroup contains the identity, so the identity will always be in H. Keep that in mind. And also we are having H dash, which is a subgroup of G dash. And also what do we have? If you see the theorems, we are also having the kernel. The kernel will be a subgroup of G. It will have some intersection with H because all subgroups contain the identity. So that is why you have to draw it. It will have some intersection. It will have some other elements in common, maybe or maybe not, but at least you are guaranteed that the identity will also be in the kernel. So the identity will belong to both H as well as the kernel. And F is a homomorphism from G to G dash. So what does this theorem say? This theorem says that the pre-image of H dash, it is a set, so the pre-image of H dash is also going to be a set. This theorem says that if you take the pre-image of this set under F, it will also be a subgroup of G. Again, it will have some intersection in common, and not only that, we have that this pre-image, it will contain the kernel. So this one will be the pre-image of H dash, and it will contain the kernel. That is, the kernel will be inside this pre-image. And moreover, what do we have? We have that the image of H, this one is the pre-image of H dash, the image of this H, which we denote by FH, it will also be a subgroup, but it will be a subgroup of G dash. So this is a rough representation of what we are going to do. We are given a subgroup of G, that is H. We are given a subgroup of G dash, that is H dash. We will show that this pre-image, it will be a subgroup, and also we will show that kernel F, it is inside the pre-image, and moreover, theorem 5 deals with the image, that is the image, it is a subgroup of G dash. But again, you haven't learned what a pre-image is. In fact, pre-image and images, the concept is with functions. It is not only with homomorphisms. So if you have this set, okay, A and B, suppose you are having these elements here, just a rough idea of what an image and pre-image is. Maybe 5, 6, 7. Okay, maybe A, B, C, D. Suppose you have a function like this. 1 goes to A, 2 goes to A, 3 goes to D. It can be arbitrary as you like. Okay, and 7 goes to C. Suppose we take the set 3, 4, 5. 3, 4, 5, maybe we are taking x equal 3, 4, 5. What will be the image of 3, 4, 5? As you can see, 3, 4, 5 is over here. Maybe I will denote it with H so that you won't be confused. H is 3, 4, 5. What will be the image of 3, 4, 5? Fh, the image of H, it will be, as you can see, 3 goes to D, so it will be D. The image of 4, it is B, and the image of 5, it is C. So the image of H, it will be D, B, C. D, B, and C. This will be F, H. I hope it is clear what an image is. Okay, now we will see we will take a look at the pre-image. So if we have to take a look at the pre-image, we are going to need a set. We are going to need a subset of the second set, that is B. Okay, maybe I will take this one, AB. I will take H dash as AB. What will be the pre-image of AB? The pre-image of AB, denoted by this. Again, I don't know why that keeps on happening. So if we have to calculate the pre-image of H dash, we will see at all the pre-images of A and B. What are the pre-images of A? The pre-images of A, it has two pre-images, so it is 1 and 2. And what is the pre-image of B? As you can see from the picture, it is only 4. So as you can see over here, the pre-image of H dash, it will be 1, 2, and 4. If we have to write it down as a set, because the image and pre-images are sets. So if we have to use sets, this is how we will do it. Okay, so what are we having? We are having that pre-image of H dash. It will be a set of all elements from the first set. That is, X should be an element of the first set. Over here it will be G, because as we were doing, F is a function from G to G dash. So it will be an element of G, and Fx should be an element of H dash. Fx belongs to H dash. This denotes an element, this denotes an element, this is a set. So some of you may be confused, okay, maybe even be wrong. You may write something like this: Fx equal H dash. You have to be very careful with this, because this one is an element, Fx is an element, this one is a set. They cannot be equal. So that is why we must use this symbol, Fx belongs to H dash. And how will we define the image? And the image of H, you can define it as, the image will be elements of the second set, will consist of elements from the second set, which can be written like this: y equal Fx, x belongs to H. So this is about pre-image and image. With that idea, you can do 1, 2, 3 and 5, and I will do 4 and 6. Then let us see at this theorem number 4. Theorem number 4, it's very simple, because it is just an application of the fundamental theorem of group homomorphism. So what do we have? You must remember that we already have a function f from G to G dash, and it is a homomorphism. So how should we define this? Okay, we need to show that G by pre-image of H dash, it is isomorphic to G dash by H dash. So if we have to use the fundamental theorem of group homomorphism, we will define a function from G to this G dash by H dash, and then we will show that kernel of the homomorphism, it will be the pre-image of H dash. So this is how we will define phi. It should take an element of G, it should take it to an element of G dash by H dash. G dash by H dash, it is a quotient group. All elements of G by H, all elements of G by H, they are of the form Hx, where X is an element of G. So what can we say? So all elements of H dash by G dash, it will be of the form H dash, and this one should be an element of G dash. So that is why we are taking Fg, because if G belongs to capital G, then Fg, it will belong to G dash. So that is why we define the function like this. We have done it even in the fundamental theorem. We have done a similar thing. So that is how we will do. So once we have defined a function, if you remember the steps, we need to show that it is well defined. We need to show that it is a homomorphism, and we need to show that it's onto. Okay, so these are the steps for well defined, which I think you are familiar. So I won't go into the details. If G1 is equal to G2, just take F on both sides. You will have Fg1 equal Fg2. But again, take H dash, okay, operate by H dash form the cosets by maybe operating by H dash, and then you will have this. And this one is equal to phi G1 because of this. Phi G is equal to H dash Fg. So H dash Fg1, it will be equal to phi G1. Similarly on the other side. The next step is proving that it is a homomorphism, which I think you are familiar by now. Phi G1 G2, by definition it is this. Just say phi G, it's H dash Fg. So if instead of G you have G1 G2, so instead of Fg also you will have Fg1 G2. But F is a homomorphism, so you can split. Again, H dash is normal, product of two cosets is a coset, so you will have this. Just use the definition of phi. Again, just use this. You will have this line. Now we need to show that it is onto. We need to show that phi is onto. So what do? We just take an element from the second set. The second set, it is G dash by H dash. So that's why we start with an element from the second set. We start with this. What do we want to do? We want to show that this element has a pre-image on the phi. That is, there exists an element in the first set, which when you operate with phi, okay, you will get this element in the second set. So why it belongs to the second set? So any element of this quotient group, again, it will look in this way, H dash G dash, where G dash belongs to capital G dash, because all elements of this, they are cosets. So you will have this. But G dash, remember that F is onto, because F is onto, so G dash will be equal to Fg. So if you cannot remember what is F, F is a function from G to G dash. It is onto, right? So if you take an element G dash from over here, there exists an element G which is taken by F to G dash. That is Fg equal G dash. So that's why G dash, you can write it as Fg. So we need an element from the first set, right? This is that element from the first set. G, it is an element from the first set. Just say, how did we define phi? We need an element from the first set. We have taken an element from the second set. We need to find an element from the first set. So this element G that is from the first set, this will work. Okay, Fg equal G dash. So we are taking this element G. So phi G will be equal to the, if you follow these steps, it will be equal to the element in G dash. So that is how you do it. And the last stage is proving that kernel is equal to the pre-image. So this is how we do it, because they are sets. Kernel, it is a set. The pre-image is also a set, as you have learned. So if we will do it in the usual way, that is, first prove that one is a subset of the other and the other is a subset of the first one. So x belongs to kernel phi. So phi x will be equal to the identity of the second set. The identity of the second set is G dash by H dash. Just say the second set is G dash by H dash, as you can see here. So phi x will be equal to the identity of that. So that's why we will have phi x is equal to H dash. The identity of G by N. If you remember, what is the identity of G by N? It is NE, right? It is NE, or simply we can write it as N. So similarly, the identity of G dash by H dash, it will only be H dash. Phi x, you can write it as this, because phi G equal H dash Fg. So phi x will also be equal to this. And this is a property of cosets. Remember, Hx equal H, you can immediately write down as x belongs to H. Whenever you have this one, you can immediately write this one as the next step. So that is what we are having over here. But instead of x, we are having fx. And instead of this h, we are having h dash. So we can immediately write down this step. And this follows from the definition. If fx belongs to h dash, then x will be in the pre-image. Okay, so we can even go in the reverse. Okay, and then just use a fundamental theorem of group homomorphism. You will have the required result. The next one, what we will do is theorem number 6. Theorem number 6 is actually the most important theorem this day. Theorem number 6 is also called as the correspondence theorem. Okay, so if you have to prove that correspondence theorem, you will have to prove this. So what are we doing in this correspondence theorem? So we have the set G, and we have this one G dash, and we have a homomorphism F. F is also onto, and it is a homomorphism. This theorem says like this: you collect all subgroups of G dash. You collect all subgroups of G dash. You don't know how many subgroups in G dash there are. Okay, maybe there are 5 or 6. Okay, maybe there are 5 subgroups of G dash. And also, G, it can have so many subgroups. Okay, you may have 10, 11, 12, 13, 14, whatever. Okay, but out of all of these subgroups of G, you take only the subgroups that contain the kernel. Okay, so if the kernel is over here, okay, just take only the subgroups that contain the kernel. Okay, so what you will do, this theorem, what does it say? If there are 5 subgroups over here, you will also find that there are 5 subgroups in G, and also that these subgroups contain kernel. Of course, there may be other subgroups, but they don't contain the kernel. Again, I repeat, G dash, suppose it has 5 subgroups. This theorem says that you can find 5 subgroups of G that contains the kernel, exactly 5. Similarly, if you can find 6 subgroups of G dash, you can also find 6 subgroups of G that contains the kernel. This is actually very wonderful because this happens only if you have a homomorphism that is onto. It doesn't work otherwise. Okay, it only works if you can define a homomorphism that is onto from G to G dash. So similarly, if you have 7 subgroups of G dash, you will have 7 subgroups of G that contains the kernel. So what does it mean? Okay, if we have equal number of subgroups that contain the kernel and as well as G dash, we can define a 1-1 onto function. Okay, we can define a 1-1 onto function. Again, I repeat, G may contain other subgroups, but it will contain exactly that number of subgroups that contain G dash. So you can define a 1-1 onto function, which we have given by, if this set has 5 elements and this one has 5 elements, you can define a 1-1 onto function. Similarly, if it has 6 elements and 6 elements, you can define a 1-1 onto function. That is what we are doing over here. So what we are doing is this. Okay, just let me zoom in. We have taken X to be, you collect all the subgroups of G, but all the subgroups of G that contains the kernel. Okay, all subgroups of G that contains the kernel. And Y, you collect all the subgroups of G dash. We can find a 1-1 onto function from the set X to the set Y, or from the set Y to the set X. So how do we define it? We take, because we are defining a function phi from Y to X, psi from Y to X, so we have to take an element of Y over here, which we have denoted it by B dash. B dash, it will be a subgroup of G dash, so that we know. So it should go to an element of X, right? An element of X, and if it has to be an element of X, what does it have to be? It has to be a subgroup of G, and also the kernel must contain in A. So that is why we are doing it like this. B dash, it is a subgroup of G dash. So we are taking the pre-image of B dash. If you take the pre-image of B dash, then the pre-image will contain the kernel because of these lines here. Okay, because of the theorem 1 and theorem 2. So again, now what we need to show that it is a 1-1 onto function. So this is how we do it for proving 1-1. You start with psi b1 dash equal b2 dash. So they are subgroups of G dash. You need to show that b1 dash is equal to b2 dash. So this is by using the definition, because just say psi b dash is equal to pre-image of b1 dash. So that is what we are doing. Again, these are now sets. If they are sets, if you need to show that they are equal, you need to show that one is subset of the other and the other is a subset of the first one. So that is what we are doing. That b1 dash belongs to b1 dash. Because it is a subgroup, and because f is onto, because f is on 2, right? F is on 2, and b1 is from the second set. Okay, maybe I'll draw over here. This is G, this is G dash, F is on 2, B1 is over here, sorry, okay, B1 dash, B1 dash is over here, and similarly B2 dash is over here. So you are taking B1 from here, B1 dash. Because F is on 2, so it contains a pre-image, which we have denoted by B1. B1 will be an element of G. Just say FB1 will be equal to B1 dash. Okay, so B1 will be in the pre-image. B1 will be in the pre-image. So if you follow all these steps, you will have these lines. Okay, B1 is in the pre-image of B1 dash, but the pre-image of B1 dash is equal to pre-image of B2 dash. So that's why you will have this. So you will have this, okay, which is simple. And similarly, you can show that B2 is B2 dash subset of B1 dash. The next stage is proving that phi is on 2. If you have to show that phi is on 2, you take an element of the second set. You take an element of the second set, you will show that it has a pre-image. So what is the second set? And you have to be very careful, okay, because we are dealing with so many functions. You have f, you have phi, you have psi. Okay, so sorry, actually I made a mistake over here. It should be psi. Okay, proving psi is on 2. So if you have to show that psi is on 2, you are taking, and this is psi, so first take an element from the second set, that is x, that A belongs to x. If it is an element of x, so it will be a subgroup of G, and kernel F will be subset of A. So if you follow these steps, because A is a subgroup of G, so the image of A will be a subgroup of G dash. So FA will be a subgroup of G dash. And okay, so what we are doing here is this. Okay, you are psi is from Y to X. Okay, X, you are taking A, so you take the, so sorry, psi, just let me see, psi is from Y to X. Again, that is all right. So what do we need to do? And what are we doing? F is from G to G dash. Okay, keep that in mind. Okay, because we are having so many sets, so many functions. Okay, so let's see. G to G dash, you are having the function f. A, it will be a subgroup of G from this line. So A will be here. So what are we doing? We are taking FA here. The image of A will be in the second set, that it is in G dash. So what we will do is all elements of this set Y, if you see the definition, it will be, they should be subgroups of G dash, right? They should be subgroups of G dash. All elements of the set Y should be subgroups of G dash. So if you see this, we have taken A in X, FA is a subgroup of G dash. So it gives us an idea that we need to have this. FA will be sent to A by psi. FA will be sent to A by psi. So that is how we got the idea. Okay, some of you may be wondering, how do we know that? We will show phi, psi, sorry, it should be psi, FA equal A. Okay, psi psi b dash is equal to pre-image b dash. So psi of fa, psi b dash equal pre-image b dash. Okay, keep that in mind. So psi of fa instead of b dash, if you have fa, also you will be having pre-image fa. So these steps, because again they are sets, you just need to show that one is a subset of the other, and similarly the reverse way. So take an element x here. So just operate by f. Fx will belong to fa. Because it belongs to fa, so it will be equal to some element. This one, it just belongs to fa because this is an element and this is a set. You need some equality, so that's why we are using this one, fx equal. It will be equal to an element set, so that's why you have belongs, whereas this one over here, it is equal because both of them, they are elements for some a belongs to a. So this one is very easy now because we are dealing with groups. Just multiply with the inverse, you will have this. So xa will belong to the kernel, so you will have this. Okay, similarly you can do the reverse and you will have the required theorem. So phi will be on 2. This application of the correspondence theorem. So what have we learned? We have learned that G by n, it is a subgroup. G by n, it is a quotient group. We can easily determine subgroups of G, but if we have to determine subgroups of G by n, we have no other way. Of course, we can calculate it in the direct way, but that will be too difficult. So that's why we have this theorem. It is actually some sort of a corollary or an application of the correspondence theorem, that is theorem number 6. So n is a subgroup of G, then all subgroups of G by n are of the form H by n, where H is a subgroup of G containing n. So how will we do it? Remember that we need the function f and we need the function psi. So this is how we will do it. Define. We have maybe. Okay, maybe define also, it's all right. We have f from G to G by n. Okay, so instead of G dash, we are having G by n. Define it as fx equal nx for all x belongs to G. So what do we have? We have done this one actually. Then f is a homomorphism and also we have that f is on 2. Okay, so what are we doing? Let's see. We have this G here and we have this G by n here. So what will we do? Collect all the subgroups of G that contains the kernel. Okay, so you have to know what the kernel of f is. Okay, I will just write it down. We also have, moreover, the kernel, because we need to have an idea of what kernel is. Kernel f is equal to n. This one will be maybe as an exercise. You will have to write down all these steps. Okay, but over here, because we have already done something like this, okay, you will have to do it. You will have to show that f is a homomorphism, show that f is on 2, show that kernel f is equal to n. Okay, which is not so difficult. So over here, what will we do? We will collect all the subgroups of G that contains the kernel, that is n. And over here, we collect all the subgroups of G by n. We know that there will be a 1-1 correspondence, 1-1-on-2 correspondence between these and these. Okay, by the correspondence theorem, there is a correspondence or a 1 onto function from the set of all subgroups of G that contains the kernel and all the subgroups of G by n. So what will we do? We will show that we need to show that all subgroups, just like the theorem says, of G by n are of the form H by n, where H is a subgroup of G and and n is a subset of H. So how do we do it? Okay, we have got that onto homomorphism that we really need. So this is how we will do it. Now it won't take too long. We start with a subgroup of G by n, that is H dash. How will we get a subgroup of G? Because we have a function and we have an onto homomorphism, you can easily take the pre-image. Okay, take the pre-image of H dash. Okay, take H to be equal to the pre-image of H dash, because we need a subgroup of G and we need that n subset of H. So that is why we are taking H to be the pre-image of H dash. This one, n will be inside, okay, because of the previous theorem that we have done. So take H equal pre-image H dash. Then H will be a subgroup of G because of the previous theorems. Pre-image of a subgroup is a subgroup, and n and kernel F subset of H, but the kernel over here in this case it is n. So now all that is left to show is this. We need to show that H dash is equal to H by n. That is H dash equal pre-image. We have taken H to be this by n. Okay, so how will we do it? Again, there are sets. We can do it in the usual way, or we can do it like this. H dash. H dash, it will be a subgroup of G by n, right? H dash is a subgroup of G by n, so that's why it will be of the form, it will be a coset. It will consist of cosets. So H dash, it will consist of cosets. Again, we are dealing with G by n, so that's why we are having nx, where x belongs to G. It looks like we won't be able to reach anywhere. Okay, maybe it will be a bit difficult. So instead of showing that H dash is equal to pre-image H dash by n, instead what we will do the reverse, which is again still valid because we are dealing with equality. So this is also a coset. It will be of the form n x, where x belongs to pre-image H dash. So it will consist of cosets. X belongs to pre-image H dash, right? So nx, where fx belongs to H dash. X belongs to pre-image H dash, so fx will be in H dash. So we are having this, but if you look at the definition of x, remember fx is equal to nx, right? Fx is equal to nx from the definition of f. So we are having x will be equal to fx, where fx belongs to H dash. So fx belongs to H dash. So we can easily write this one as x x is equal to fx and fx belongs to h dash, so we can immediately write down this one, x such that x belongs to h dash. So this is how we will do it. Okay, x belongs to h dash, so you can easily write this one as h dash. That is enough for today.